In this lesson, we will discuss the case of the motion of connected masses. I have two trolleys here. I have connected them by means of a string. If I apply a force on one of them, you notice that the force applied on the first will make it move, and then it will stretch the string. There will be a tension on the string. And what will happen? Well, my string fell off. Well, the tension on the string is going to pull the next mass. Now, therefore, what will be the net force on the trolley in front? The force I apply will be forward, and the tension at that time, the tension on the string is going to pull this trolley back. So the net force on this trolley will be the applied force forward minus the tension on the string. And that net force will produce an acceleration on this object. Now, what will be the net force on the second trolley? It will be the tension on the string, because it is the tension on the string that pulls the second trolley. Now, when you deal problems like this, connected object, what you need to do is isolate each object, figure out the net force on it, and then set the net force equal to ma. So isolate this object, the net force on it will be the applied force forward minus the tension force. That will be equal to mass times acceleration of this trolley. For the second trolley, the force on it is the tension, and that will be equal to its mass times its acceleration. Now tell me, if this system is made to move with an applied force like this, what will be the acceleration of each of these? It will be the same. Well, this is one type of connected masses we will be looking at. Another type of connected masses we will be looking at will be this, where you have a pulley and two masses are suspended by means of a string. Alright, and if the masses are not the same, you can see there will be relative motion. Is that right? Now, this is slightly heavier, so that's going to move down. Again, we apply the same principle. We take each object and find the net force on it. Now tell me, what is the net force on the object that I'm holding now? Well, the weight of this object will be acting vertically down, and the tension on the string will be pulling it up. And in this case, that tension is going to win. You can see the tension is pulling it up. On the other hand, the one on the right, the weight will be acting down and the tension will be acting up. But the weight is greater, therefore the net force on this will be the weight minus the tension. Alright, I'm talking about the magnitude only, not the direction. So in each case, obtain the net force and set the net force equal to ma, and that will help us to solve problems. Okay, let's look at each of these. So, in order to solve problems using connected masses, we first isolate each object, identify the forces acting on each of the objects, and then apply the laws of motion in each case. Well, of course, the law of motion is the net force equal to ma, and we produce equations and solve those equations for the unknown. Let's take a simple example. 3 blocks are pulled along a frictionless horizontal surface, applying a force of 18 Newton as shown here. Now there are 3 trolleys here. They are connected by means of, you can see that yellow that is there is the string. And applied force 18 Newton pulls the system forward. What do we need to find? What is the acceleration of the system? Now, when you consider the system, the whole system has a total mass of m1 plus m2 plus m3. And that total mass is being pulled by 18 Newton. So how will you find the acceleration of the system? Alright, I'm going to leave it for you. And what are the tension forces on each of the pieces of strings? What is the tension on this string? And what is the tension on this string? Okay, let's first deal with the first case. What is the acceleration of the system? Let's say the tension on the string connecting the mass m1 to m2 is T1. And you notice that the direction of T1, when you look at the motion of m2, that T1 is pulling it back. Whereas when you look at the motion of m1, T1 is pulling it forward. And the string that is connecting m2 and m3, let the tension be T2. And look at the directions of that T2. When you consider the motion of m3, that T2 is pulling it back. Why? Because that T2 is pulling these 2 masses. That means it is pulling this m3 back with that T2. But when you look at the motion of m2, that T2 is pulling it forward. So you must be able to understand the directions of these tensions. Now notice here that T1 pulls m1 to the right and m2 to the left. I hope that is clear. The tension on the string connecting the masses m2 to m3 is T2. T2 pulls m2 to the right and m3 to the left. The total force F net equal to 18 Newton pulls the whole system of mass m equal to 1 plus 2 plus 3, that is 6 kilogram, and therefore you can now use F net equal to ma and find the acceleration of the system. A equal to F net over m, that will be 18 Newton divided by 6 kilogram, and that is 3 meter per second squared. The acceleration of the system is 3 meter per second squared. What does that mean? It means the acceleration of each of these masses is 3 meter per second squared. The acceleration of m1 is 3 meter per second squared. The acceleration of m2 is 3 meter per second squared. The acceleration of m3 also is 3 meter per second squared. Okay. Now we take each mass separately. Identify, well, separate each mass and identify the net force on it. Let's take the 1 kilogram mass, the one at the very back. The only force acting on that is the tension T1 pulling it forward. Is that right? That's right. So F net on this mass is T1. The tension T1 produces an acceleration of 3 meter per second squared on this mass of 1 kilogram, and therefore we know that F net equal to ma, T1 equal to, T1 is the net force, and that is equal to ma, mass is 1 kilogram, acceleration is 3 meters per second squared, so T1 equal to 3 Newton. Alright, let's now talk about M2. What are the forces acting on M2? Well, T2 is pulling it to the right and T1 is pulling it to the left. Is that right? This tension T1 will be pulling M2 to the left and the tension T2 will be pulling it to the right. So to find T2, we isolate M2. The forces on M2 are T2 to the right, there you are, and T1 to the left. Therefore, what is the net force on that mass? The net force is T2 minus T1, and that net force must be equal to M2 times A. M2 is 2 kilogram, acceleration is 3 meters per second squared. So T2 minus T1 is 2 kilogram times 3 meters per second squared. That is 6 Newton. We know T1 already. Is that right? We calculated T1. You remember how much was it? It was 3 Newton, wasn't it? So T2 equal to T1 plus 6 Newton, and therefore T2 equal to 9 Newton. Alright, I think we now found the tensions on each string. You can see how simple the problem becomes once you isolate each object, identify the forces acting on each, and then apply the law of motion, and we can calculate the unknown forces. Alright, next we will look at connected masses. Now this, I just showed it to you how the system looks like. Well, let's have a look one more time how disconnected mass looks like. Let's talk about the motion of this system. Now, I'm talking about my side. Now, there is a mass on the left, there is a mass on the right. The mass on the left I'm going to call M1, and the mass on the right I'm going to call M2. Now tell me, the tension on the string, will the tension on the string on each side be the same? Well, it will be, provided there is no friction on this pulley. So the tension on the string on the right and on the left are the same. Alright, now tell me, the mass on the left is M1. What is the net force on this mass? I told you that the net force is its weight. What is the weight of M1? M1G, is that right? And there's a tension force acting up. And since it is moving up, we know the tension force is greater than the weight. So we can say the tension minus the weight equal to, that is the net force on it, equal to MA, where M is this mass and A is the acceleration. Similarly, we come to this mass, we can say M2G is the weight acting down and the tension is the force acting up. And in this case, the weight is winning, and therefore we say, remember, we are only looking at the magnitude, not the direction. The weight acting down is a greater force, so the weight minus the tension equal to M2A, mass times acceleration. And is the acceleration of these two masses the same? Yes. There you are. The magnitude of the acceleration is the same in both cases. We can actually obtain equations using these two masses and calculate the tension on the string and the acceleration of the system. Alright, let's in the example here I have used specific masses. They say two masses, M1 equal to 100 gram and M2 equal to 101 gram are connected by a string that passes over a frictionless pulley. Find the acceleration of the masses and the tension in the string. Well, how do we start doing this? Since the same string supports the two masses and there is no friction on the pulley, the tension of the string on the left and on the right, it is the same string, therefore the tension is the same and we call it T. And now we isolate the masses M1 equal to 100 gram. Always remember to convert it to proper unit. M1 equal to 0.1 kilogram. The weight of M1 is M1 times G, that is 0.1 kilogram times 9.8, that is 0.98 Newton, acts vertically down. So M1G, the weight of that first mass, which is 0.98 Newton, is acting vertically down. What other force is on M1? The tension T on the string is acting vertically up. Alright? Since M2 is greater than M1, I have made M2 greater because M2 is 101 gram. That means M1 is likely to move up and M2 is likely to move down. Therefore, can you tell me what is the net force on M1? If M1 is going to go up, T is going to win. That means T minus M1G, T minus M1G, which is T minus, you can see we calculated M1G. M1G is 0.98 Newton. So the net force on M1 is T minus 0.98 Newton. And if A is the acceleration of the system, then we have F net equal to MA. What is our net force? It is T minus 0.98. And so T minus 0.98 equal to MA. M is 0.1 kilogram. So we have one equation using the motion of the mass M1. And similarly, you can write another equation for the motion of mass M2. Can you write that equation on your own? What is the net force on the mass M2? We carry this equation with us. T minus 0.1A equal to 0.98. That is the equation we obtained from the motion of M1. Alright? To obtain another equation, we isolate M2. The weight of M2, what is the weight of M2? M2G. Now, M2 is 101 gram, that is 0.101 kilogram. Multiply that by G and you get the weight is 0.99 Newton. And that acts vertically down. M2G equal to 0.99 Newton is acting vertically down. What is the force on it acting up? The tension T is acting vertically up. Therefore, what is the net force? The net force is M2G minus T, or M2G we know is 0.99. So the net force on the mass M2 is 0.99 minus T. Well, this net force must be equal to the mass M2 times its acceleration. So, you got 0.99 minus T equal to 0.101, and that is the net force on M2 equal to MA, is that right? The net force 0.99 minus t equal to 0.101 times A. I forgot that A there. The net force equal to MA, 101A. So you need to write that A there. Okay, but I have used that in here. Rearrange the equation. You get, always when you write equations like this, take all the variables to the left side and keep the constant numbers on the right. So what we will do is take the negative t to the right. You get 0.101a plus t, that is this. 0.101a plus t equal to 0.99. We got two equations. Can you solve these two equations? Well, that's not difficult. Now, let me write down those two equations. The first equation is t minus 0.1a equal to 0.98 and t plus 0.101a equal to 0.99. Now, is it easy to solve these two equations? Really, you don't need to go to the calculator to do this one. It's very simple. Because the coefficients of t in each case is 1. You can subtract one equation from the other. Well, let's subtract the equation on the top from the equation at the bottom. Alright, watch me do that. T minus t will be 0. Now, 0.101a minus negative 0.1a. You notice that I'm subtracting the top equation from the bottom. So, subtract 0.101a minus negative 0.1a becomes 0.101a plus 0.1a. And that will be 0.20a equal to 0.99 minus 0.98 is 0.01. Let me write that down for you. So, subtracting the top equation from the bottom, we get 0.101a minus negative 0.1a equal to 0.99 minus 0.98, and that will be 0.101a plus 0.1a equal to 0.01. Did I get it right? Okay, now that gives me 0.201a equal to 0.01, and now you can calculate the acceleration. A simple way to solve this equation. So solving these equations will give t equal to 0.985 Newton and the acceleration a equal to 0.05 meter per second squared. Well, I want you to do this on your own. Solve these equations on your own and make sure you get these values. If you don't get them, let me know so that I can check my values. Alright? Always make sure that any calculation that I do, you recheck it. Okay, and this is an important class of problems in physics, connected masses. In fact, it is a setup like this that was first used by somebody called Atwood to measure the value of acceleration due to gravity. Now what he did is, let me show you what he did. To do the experiment to measure the acceleration due to gravity, let's look at the theory again. If this is m1, the net force on that will be T minus m1g, and that will be equal to m1a. Similarly, the net force on this will be m2g minus t equal to m2a. We got two equations there. Now what happens if I add them? If you look at this, adding them, t and negative t will go. So on the left side, I have m2g minus m1g. And I'm going to write it like this. G times m2 minus m1 equal to, we added the left side, add the right side, we get a times m1 plus m2. And solve it for g. G equal to m1 plus m2 divided by m2 minus m1. Is that right? m1 plus m2 divided by m2 minus m1. That quantity multiplied by a. Now that means we now need to measure the acceleration. Now look at the way I'm setting up the experiment. I'm starting with the two masses the same. You see that? They're not moving. And I'm going to make m2 100 gram greater than, I'm putting 100 gram there, and I'm going to take it to a height h. And this height I just measured is 45 centimeter. So let me write down that for you, if I can find my marker. The height h equal to 0.5 meter. Okay. Now, if I let it fall, it is going to fall through this height. And I'm going to measure the time taken for that to happen. Let me get my stop clock. I'm using an old Chinese clock here, and it's not going to be very easy to measure the time. So I'm going to take it to the height h. Alright, let it go and start the clock. And stop. Well, it's a very small time. I measured the time as 0.7 second. Now, you know that when an object is allowed to fall through a height h, that h will be equal to 1/2 at squared. Therefore, that a will be equal to 2h divided by t squared. Alright, so what I'm going to do is replace the a here. Look at this, I'm going to take off that a there and write it as 2h divided by t squared. Now let's calculate g using these values. m1 plus m2. Now there's 100 gram, 100 gram, 100 gram, 300, 400, 500, 680 grams is all together m1 plus m2. So I'm going to say that will be 0.68 divided by, what is m2 minus m1? 100 gram. And that will be times 2h, 2 times 0.45 divided by t squared, 0.7 squared. Can you calculate that for me? Well, I'm going to calculate that along with you. 0.68 multiplied by 2 times 0.45 divided by 0.1 multiplied by 0.7 squared. Well, that gave me a fairly large value. That means the time. Now, I thought my time was very close to 0.9 seconds. Well, if I change that time to 0.9 seconds, well, it gives me about 8. So, well, if I take an average of 0.7 and 0.9, I get 0.8. and that will give me close to 9 meter per second squared. Now remember, what I did is very crude, but you can use this equipment to measure very accurately the value of acceleration due to gravity. So this equipment is now called Atwood's machine because it was used by Atwood to measure the acceleration due to gravity. We will now consider motion of an object placed on an inclined plane. What is an inclined plane? Well, an inclined plane is inclined to the horizontal. Is that right? Here I have an inclined plane. I can change the inclination of the plane to any angle I want, and you can see the angle can be measured here. Well, I'm going to take it and keep it facing me so that you can see the whole of the inclined plane. Now, if an object is placed on a plain horizontal surface, tell me what are the forces acting on this now? You should be able to tell me this. The weight of this block will be acting vertically down. In fact, the force that is pressing the block onto the plane, this is the plane surface, the force that is pressing this block to this surface is the weight of this block. And what does the plane surface do in turn? Apply a force upward. What do you call that force? The normal force. So if I draw that on the board, it will look like this. Now this is the plane surface. Let me take off this. Now if this is the plane surface and here is the block, the weight of the block mg will be acting vertically down, and the plane surface will therefore apply a normal force which will be upward. Now there is no net force on the object now. Alright, I want you to watch what happens when I tilt this plane. Now this is an inclined plane. Now the weight of the block now is doing two things. What are the two things it does? It pulls the block down the plane, that is one part of the weight. The other part is pressing the block onto the surface. And I want you to watch this again. When the inclination is 0, all the weight is pressing the block onto the surface. But when I increase the inclination, well, the weight actually does two things. One, part of the weight pulls this block down the plane. Look at that, it's moving. And also it is pressing onto the surface. So the weight now has two components. I will draw that as we go on. Now what are the two components? There is one component of the weight acting down the plane like this, and there is another component that will be acting at right angles to the plane like this, pressing the block onto the surface. So one more time, this weight of this block has a component down the plane and a component at right angles to the plane. Okay, now as you keep on increasing the inclination, the component down the plane will increase and the component pressing the block to the surface will decrease. See that? And finally, when the angle is 90 degrees, you can see all of the weight is moving down. There is no force pressing the block onto the surface at all. So let's quickly do it one more time. When the angle of inclination is 0, all the weight is pressing the two surfaces together. As the inclination increases, the component of the weight down the plane increases and the component pressing the two surfaces decreases. Now you can see the component down the plane increases and the component pressing the two surfaces decreases, and finally when the angle is 90 degrees, all of the weight is pulling it down the plane. There is no force pressing the two surfaces at all. Well, let's now put these things together and look at the theory of inclined plane. Alright, let's consider a mass M resting on a plane surface. Its weight mg acts vertically down. There you are. Now this is the force pressing the object to the surface, as I just showed it to you. Now what happens if the plane is now tilted to form an inclined plane of inclination theta like this? Well, the weight mg is still acting vertically down. You see, no matter how you place an object, its weight will be always vertically down. So what is the direction in which I can draw the weight vector? Look at this. The weight is acting vertically down. Only part of this weight is now pressing the two surfaces together. The other part is pulling it down the plane. Now a line drawn at right angles to the plane, look at this. A line drawn at right angles to the plane makes an angle with the direction of the weight. Can you tell me what is this angle equal to? That is the angle between the vertical, that is the direction of the weight, and a line drawn at right angles to this plane. That angle will be the same as this angle. Now how do you know? It's a simple geometry. Let me explain that to you. There is a result in geometry that says if you have two lines that make an angle theta. Now draw a line perpendicular to the first line. There you are. And draw another line perpendicular to the second line. There you are. So you notice that these are the two initial lines making an angle theta. I drew a third line perpendicular to the first line, then a fourth line perpendicular to the second line. Now the result says the angle between the first two lines will be the same as the angle between the lines 3 and 4. In other words, lines 1 and 3 are perpendicular, lines 2 and 4 are perpendicular. Therefore, angle between lines 1 and 2 equal to the angle between lines 3 and 4. Now the same here. If this is one line and this is the second line, let me draw that for you here. Now this is the line 1. I'm going to call it line 1. And this is line 2. Now line 3 is at right angles to line 2. And line 4 is at right angles to line 1. Therefore, the angle between lines 1 and 2 equal to angles between lines 2 and 4. This angle. Well, okay, so that means this angle is the same as theta. Okay, in that case you tell me, you know how to find the components of a vector. Here we have a vector that makes an angle theta with this line. Now this vector has a component along that line and a component along the plane. Can you tell me what those components are? What is the component of this weight mg? at right angles to the plane along this line. Since this angle is theta, that component will be mg cos theta. The vector component of mg at right angles to the plane is mg cos theta, and the vector component of mg down the plane is mg sin theta. Very, very important results. You cannot ignore it. All right? Let me bring back my inclined plane and let's have a look at it. Well, now here is the inclined plane. What is the direction of the weight? The weight will be acting vertically down. The component of the weight acting down the plane will be mg sin theta, and the component of the weight that is pressing the two surfaces together at right angles will be mg cos theta. And you know, as theta increases, cos theta decreases and sin theta increases. You can see mg sin theta increases and mg cos theta decreases. You understand that? So this phenomenon is very important. The weight of the block will be acting vertically down. Its component mg sin theta acts down the plane, and the component mg cos theta is pressing the two surfaces together. Okay. So, the component mg cos theta presses the object onto the surface. The surface in turn applies the force of reaction. You see, this mg cos theta is pressing this surface at right angles, and the surface in turn applies the force of reaction, which is equal but opposite to mg cos theta. There you have the force of reaction, which we are going to represent as F sub n, the normal force. So this is the normal force, which is the same as mg cos theta, but directed in the opposite direction. There is no net force at right angles. You see, there is no net force in this direction. Therefore, we can say the normal force F sub n equal to mg cos theta. And what does mg sin theta do? Mg sin theta pulls the object down the plane. Now, this is the net force on the object. Here, we assume that there is no frictional force between the block and the plane. In the next lesson, we are going to look at friction. So then we will change our story. But today, there is no friction between the block and the plane. Therefore, mg sin theta is the net force pulling the objects down the plane. And it produces an acceleration A on the object down the plane. So we know that the net force equal to ma, F net equal to ma. And that means the net force is mg sin theta, and that mg sin theta equal to ma. And therefore, A equal to g sin theta. When you keep an object on an inclined plane, it will accelerate down the plane, and what will be its acceleration? Will be equal to g sin theta. So there is a difference between a freely falling object. A freely falling object has an acceleration g. Whereas if the object is moving down the plane, its acceleration will be g sin theta, where theta is the angle of inclination. And when the angle theta increases, the force pressing the object to the surface will decrease, and the force pulling it down will increase, as I just showed it to you. Is that right? Okay. I'm going to stop with this part of the lesson here. I will record a second part where we will use these concepts to solve problems. That's what we normally do. We will be using the concepts we developed in the theory part to solve problems. Alright, I will see you for that part a little while later.